Hi, welcome to Math. One of the most important aspects of graphing polynomials is its end behavior. But let's talk first about what does behavior mean. So the behavior of a function is analyze what the y values are doing as we consider different x values. We have already studied this type of behaviors when we did local maxima and minima, when we analyzed intervals of increase and decrease. You see, when we say 4 is the local minimum, it's because we are analyzing the behavior of the function around 4. And we notice that at 4, we have a point that is the lowest in that little piece of the graph. This is analyzing behavior of the function, what the y values are doing near 4, and we call this local behavior. We also analyze behavior of a function when we were talking about increasing and decreasing intervals. We can ask ourselves a question. What is the behavior of the function on the interval negative infinity to this point here? Let's call it, a. So what is the function doing on the interval negative infinity to a? So we see the trajectory of the function and we see, okay, the function is going up and we called it increasing. So this is what we refer to when we are talking about behavior. Now, end behavior of a function is what happens to the function towards the end of the graph. So we're looking at what our y values doing as x gets really big. So we are going to analyze towards the end as x approaches infinity and the other end as x approaches negative infinity. And then we look at the y values. Well, if x gets really, really big, then y is going up, and we say that y is approaching positive infinity because it's going up all the way to bigger and bigger values of y. In this example, we describe the end behavior in the following way. As x approaches infinity, y approaches infinity. And on the other side of the graph, we describe as x approaches negative infinity, our y values are going down. They're getting smaller and smaller and smaller and smaller. So as x approaches negative infinity, y is approaching negative infinity. You see, it's going down, going to negative infinity. And that's the end behavior of that example. Now let's describe the behavior of this polynomial function. Let's call it p of x. Now our polynomial function has a name, and we analyze it using the name of the polynomial. So it's the same thing. And as x approaches infinity, the y value is approaching infinity. But we're not going to call it y, we are going to call it p of x. So we say p of x approaches infinity. So to describe the end behavior of the function as x approaches infinity, you would say as x approaches infinity, p of x approaches positive infinity. And on the other side, we describe it as x approaches negative infinity, our y values are approaching positive infinity. But the name is p of x, so to describe it, we say as x approaches negative infinity, p of x approaches positive infinity. We talk now about end behavior of power functions. Functions that looks like a times x to the n. If n is even, graph right here, and a equals 1, we have all these polynomials that you can see the graph. So x to the 6th power, x to the 4th power, x to the 2nd power. And we notice that the end behavior of all those functions is the same. So as x approaches infinity, all of them go up. As x approaches negative infinity, all of them go up also. Also notice that if a is positive, the end behavior is not going to change. If a is positive, the only thing that could happen is that you are stretching or compressing along the y-axis, so the end behavior is going to be preserved. And then the end behavior of all power functions with a positive and n even can be described as x approaches infinity, y approaches infinity, and as x approaches negative infinity, y also approaches positive infinity. In the same way, we see that if the powers are odd, then these are the graphs of the power functions for a equals 1. They all have the same end behavior. And again, if a is positive, the end behavior is not going to change. So we see that for all odd powers, as x approaches infinity, y approaches infinity, and as x approaches negative infinity, y approaches negative infinity. So we can describe the behavior of all power functions to an odd power for a bigger than 0 as x approaches infinity, y approaches infinity, and as x approaches negative infinity, y approaches negative infinity. In the case that a is negative, is the same as the above ones, but reflected across the x-axis. The polynomials p equals negative x squared, negative x to the 4th power, negative x to the 6th power. They all have the same end behavior, and we can describe the end behavior as x approaches infinity, y approaches negative infinity. As x approaches negative infinity, y approaches negative infinity also. And this is going to happen to all power functions that have an even power and a is less than 0. In the same way, the end behavior of all power functions that have an odd power have the same end behavior, and we describe it as follows. As x approaches positive infinity, y approaches negative infinity, and as x approaches negative infinity, y goes up to positive infinity. And this is true for all power functions with an odd power and a smaller than 0. Summarizing, the power function a x to the n ends like a parabola opening up every time n is even and a is positive. It will end like a cubic every time n is odd and a is positive. It will end like a parabola opening down every time n is even and a is negative. And it will end like a reflected cubic if n is odd and a is negative. Now we analyze the end behavior of any polynomial function. So polynomials are written in general as you see. A polynomial written in this way is going to behave the way an x to the n behaves. You see, if x is really big, then ax to the n is so much bigger than the rest of the terms to the right that we can discard them. Compared to an x to the n, they are too small. And this is happening for really, really big values of n, either big positive or really, really small negatives. So a polynomial's end behavior is given by the leading term. For example, the end behavior of the polynomial p of x equals 2x cubed plus 3x minus 1 is given by 2x cubed. So this polynomial's end behavior is the same as 2x cubed, which we know. This is an odd power, positive, so it ends like a cubic. And we describe the behavior as follows. As x approaches positive infinity, p of x approaches positive infinity, and as x approaches negative infinity, p of x approaches negative infinity. Let's look at the polynomial q of x. It's going to behave as its leading term, negative 3x to the 4th power. How is the behavior? Well, it's like a parabola opening down because we have an even power and it's negative. So its end behavior looks like this, and we describe it as x approaches positive infinity, q of x approaches negative infinity, and as x approaches negative infinity, q of x approaches negative infinity. And that's all. This is end behavior. Thank you.